Scientists say there is a 99% chance of a strong or major quake in Southern California in the next 30 years.
And we now know that the San Andreas Fault is locked, loaded, and ready to rumble.
Oh.
We now realize that the people of Los Angeles are living on borrowed time.
Recently, the San Andreas Fault has been causing sleepless nights for scientists. Something significant appears to be happening beneath this 800-mile geological feature running through California. Experts are warning that danger could be brewing along the fault line, and all Southern Californians should take notice. A massive earthquake could strike at any time. This growing concern is being fueled by a recent NASA warning, which has detected a rapidly increasing strain along the fault line, potentially signaling a looming disaster. What does this all mean? Is the San Andreas Fault gearing up for another earth-shaking surprise? Join us as we dive into the alarming news about what could be happening along the fault. Imagine waking up each day knowing you're living on a ticking time bomb. For those near the San Andreas Fault, this is a constant reality. Living close to such a fault means facing the ongoing risk of seismic activity, earthquakes that can topple buildings, destroy infrastructure, trigger landslides, and even spark wildfires. In areas where the soil is water-saturated, there's also the danger of liquefaction, where the ground turns to liquid and buildings sink. And if that's not enough, earthquakes can trigger tsunamis and be followed by traumatic aftershocks. But this is no longer a scenario we have to imagine, it's reality. The recent earthquakes in the Sierra remind us of California's very active seismic zones. When most people think about earthquakes, the San Andreas Fault often comes to mind, and for good reason. Something alarming is indeed unfolding in California. Using advanced satellite and GPS data, NASA has detected significant strain building up along the San Andreas Fault, which is sparking widespread concern. This strain points to the possibility of a major earthquake, and here's the frightening part. In some areas, stress levels are 10 times higher than previously estimated. As serious as this is, there's more. NASA's findings indicate the potential for a magnitude 8.2 earthquake, one of the highest possible on the Richter scale. An earthquake of this size could cause devastation beyond imagination. Let's take a closer look at the San Andreas Fault to understand why scientists are so alarmed. The San Andreas Fault isn't just a single crack in the earth. It's a complex system of fault lines that marks the boundary between the Pacific and North American tectonic plates. Stretching over 800 miles through California, the fault is divided into three main sections: northern, central, and southern. The northern segment, which runs from the San Francisco Bay Area to Parkfield, was responsible for the infamous 1906 San Francisco earthquake. This devastating quake, estimated at 8.3 on the Richter scale, nearly leveled the city. The central segment, known as the creeping section, stretches from Parkfield to Hollister and moves more slowly, reducing the likelihood of large earthquakes. However, the southern segment, running from the San Bernardino Mountains to the Salton Sea, is notorious for generating powerful quakes. One of the most destructive earthquakes in the fault's history was the Great San Francisco earthquake of 1906, with a magnitude of 7.8. It wreaked havoc, killing over 3,000 people and leaving more than 200,000 homeless. On April 18, 1906, the San Andreas Fault ruptured, shaking San Francisco for nearly 60 terrifying seconds. When the shaking stopped, the disaster was far from over. Massive fires broke out, further compounding the destruction. Another significant event was the 1989 Loma Prieta earthquake, which registered at 6.9 on the Richter scale. This quake caused sections of the San Francisco-Oakland Bay Bridge to collapse, claimed 50 lives, and inflicted severe damage across the region. Then, on January 17, 1994, Los Angeles experienced the Northridge earthquake. This 6.7 magnitude quake caused $30 billion in damage, killed 50 people, and left thousands injured. Despite these destructive events, the San Andreas Fault remains highly active. Just a month ago, a 5.3 magnitude earthquake struck near Bakersfield, hitting around 9:09 a.m., about 14 miles southwest of Lamont. This quake shattered windows and caused structural damage, and it was followed by at least 27 aftershocks. This earthquake is just one of several recent seismic events in California, raising concerns about increasing seismic activity. Unfortunately, scientists aren't offering much comfort. Instead, they are warning of more potential disasters in the future. With a history of catastrophic earthquakes, especially along the San Andreas Fault, it's vital to understand the science behind these events and pay close attention to expert warnings. The next big quake could be just around the corner. The next major earthquake could be just around the corner, and the devastation may surpass anything we've witnessed before. But what are the mechanics behind the type of earthquake we might be facing? Earthquakes are caused by the movement of tectonic plates beneath the Earth's surface. These movements are often gradual and go unnoticed, but over time they build up enormous amounts of energy. When that energy is suddenly released, it results in an earthquake. A prime example of this process is along the San Andreas Fault, where the Pacific plate shifts northwest at about 2 inches per year, while the North American plate moves southeast at a slower pace. As these plates grind against each other, stress accumulates along the fault line, eventually releasing energy in the form of an earthquake. Understanding how earthquakes work provides insight into the current situation with the San Andreas Fault. Recently, NASA raised concerns about the potential for a significant earthquake in the near future. Using data from GPS stations and advanced satellite imaging, NASA's findings reveal that stress has been building up along various parts of the fault, particularly in the southern section. This area hasn't experienced a major earthquake since the 1857 Fort Tejon earthquake, making it long overdue for a large quake. By comparison, the northern segment had its last major quake in 1906, and the central section saw one in 1857. Southern California's segment, however, hasn't had a major event since 1690. As stress continues to build, the likelihood of a catastrophic earthquake increases. One of the challenges in studying the San Andreas Fault is that it's not a single continuous fault line. Instead, it's a network of smaller, interconnected faults, which makes its behavior complex and difficult to predict. This complexity complicates efforts to forecast earthquakes, even with the advanced monitoring and early warning systems in place today. NASA's findings have increased public awareness of the risks associated with the San Andreas Fault and underscored the importance of continued research into seismic activity. While scientists can't predict exactly when an earthquake will occur, they are working diligently to understand and monitor the fault's behavior. NASA, along with other research institutions, uses advanced satellite technology and ground-based sensors to track tectonic plate movements, ground deformation, and other geological changes that may indicate growing stress along the fault. One key discovery from this research is the identification of slow slip events along the fault. These slow slips involve gradual, nearly imperceptible movement over weeks or months. While these events don't cause large earthquakes on their own, they contribute to the overall buildup of stress, which increases the potential for a more destructive earthquake in the future. In short, while scientists can't predict the exact timing of seismic events, the mounting evidence suggests that a major earthquake along the San Andreas Fault could be closer than we think, and the implications are not just local, but global. We're constantly hearing about the next big earthquake, and now scientists are warning that areas around the San Andreas Fault could experience a strong quake as soon as this year. NASA's Earth Science Division, in collaboration with other research institutions, monitors regional changes to better understand seismic activity. They use advanced techniques like interferometric synthetic aperture radar, INSAR, to detect even the slightest movements along fault lines, providing crucial data about how stress builds and is released over time. NASA's Jet Propulsion Laboratory, JPL, plays a central role in creating models and simulations to predict earthquake behavior and assess seismic risks. These models are powered by a combination of satellite data, field measurements, and geological studies, which significantly improve the accuracy of risk assessments. This research has greatly deepened our understanding of the complex processes driving earthquakes along the San Andreas Fault, and has also led to improved early warning systems. In addition, NASA's findings have enhanced disaster preparedness efforts in California. Public outreach and educational campaigns are vital in raising awareness about earthquake risks, ensuring communities are equipped to respond effectively during a major event. NASA actively participates in these efforts, helping individuals and communities reduce earthquake risks and strengthen their resilience. However, the complexity of the San Andreas Fault continues to challenge scientists. New discoveries constantly reshape our understanding of the fault system. For instance, a newly identified seismic hotspot has been found off the Sunshine Coast, deep within one tectonic plate. Recently, scientists discovered a previously unknown fault line adjacent to the San Andreas Fault, sparking both interest and concern. This discovery was made using advanced geological surveys and imaging technologies, including laser pulses and satellite imagery. By mapping surface features in detail, scientists detected a subtle geological formation indicating the presence of this new fault line. The discovery raises important questions, especially about how this new fault might interact with the larger San Andreas Fault system. Understanding these interactions is crucial for assessing the seismic hazards posed by both fault lines. Fault lines don't operate in isolation. They interact with nearby faults, influencing earthquake behavior in ways that remain only partially understood. The interconnected nature of these seismic systems underscores the need for continuous monitoring and research. This new fault line discovery also offers valuable insights into Earth's ongoing geological evolution. Studying these formations deepens our understanding of how tectonic processes shape the Earth's surface and influence earthquake behavior over time. With these advancements, it's clear that the next major earthquake could strike sooner than we think. The ongoing study of these fault lines is crucial for better understanding and preparing for future seismic events. By studying the newly discovered fault, scientists hope to gain valuable insights into the past behavior of the San Andreas Fault and improve predictions for future seismic events. The discovery has sparked both intrigue and urgency within the scientific community. Seismologists and earth scientists are eager to understand how this new fault might influence seismic activity along the San Andreas Fault, particularly given its history of producing large earthquakes. There is significant interest in determining whether this new fault could trigger or amplify future quakes. Addressing these concerns requires collaboration between government agencies, researchers, and local communities. By working together, they can assess the risks posed by the new fault and develop effective preparedness strategies. Open communication and data sharing are essential for incorporating this new information into existing risk assessments and hazard preparedness plans. Pooling resources and expertise will allow scientists and policymakers to better evaluate seismic risks and reduce the impact of future earthquakes. In response to the discovery, monitoring efforts in the region have intensified. The USGS earthquake map now shows increased seismic risk in the area, indicated by large red zones where damaging earthquakes are more likely. Scientists are using seismometers and other monitoring devices to detect any signs of increased movement or activity along the fault lines. Additionally, they are engaging with local stakeholders to raise awareness of the discovery and highlight the importance of earthquake preparedness. Public education initiatives, community forums, and media outreach campaigns have been launched to help local populations understand the risks associated with this new fault and to improve earthquake resilience strategies. As uncertainty about the fault persists, gaining a deeper understanding of seismic science and fault dynamics becomes increasingly critical. A key concept in fault dynamics is fault slips, which occur in three main types: normal faults, reverse or thrust faults, and strike slip faults. In normal faults, the hanging wall moves downward due to extensional forces, while in reverse faults, the hanging wall moves upward due to compressional forces. Strike-slip faults, such as the San Andreas Fault, involve horizontal movement along the fault, either right lateral or left lateral, depending on the direction of tectonic forces. Another important aspect of fault dynamics is segmentation. Fault lines are often composed of multiple segments, each of which can behave differently. Some segments may accumulate stress for long periods without experiencing an earthquake, while others may release stress more frequently, leading to variations in earthquake magnitude and frequency. Understanding the behavior of individual fault segments is crucial for predicting seismic activity, though it also adds complexity to the task of forecasting earthquakes. As research continues, scientists are working to better understand these dynamics and how they relate to both the San Andreas Fault and the newly discovered fault. By improving our understanding of these complex systems, we can enhance earthquake preparedness and minimize the potential impact of future seismic events. Advances in technology have significantly enhanced scientists' ability to study fault dynamics and predict seismic events. High-resolution satellites, GPS systems, and light detection and ranging (LiDAR) surveys enable researchers to accurately map fault systems. These tools also improve the efficiency of early warning systems, giving communities crucial time to prepare for earthquakes when seismic activity is detected. Geologists gain valuable insights into fault dynamics by studying rock formations, fault geometry, and regional stress fields. These factors help them understand the history of seismic activity along fault lines and assess the likelihood of future earthquakes. Field research often involves examining displaced landforms and layers of sediment which contain evidence of past earthquakes. By analyzing this geological data, scientists can better forecast when and where future seismic events may occur. The discovery of a new fault line adjacent to the San Andreas Fault adds complexity to an already challenging field of study. The San Andreas Fault, long overdue for a major earthquake, has remained relatively quiet for more than a century. Scientists now believe that this newly discovered fault, called the Sultan Trough Fault, might explain why. While the discovery presents new challenges, it also provides an invaluable opportunity to learn more about Earth's seismic processes and improve earthquake preparedness strategies. As research continues and technology advances, we will gain a deeper understanding of the San Andreas Fault and the seismic risks it poses, not just to California, but to the world. Monitoring and mitigation efforts are crucial for reducing these risks. Understanding the San Andreas Fault is a top priority for geologists, as it has the potential to affect millions of people. The more we learn about the fault and the forces behind its seismic activity, the better equipped we will be to protect communities and infrastructure. To achieve this, scientists rely on a combination of advanced technology and field research to monitor and analyze the fault's behavior. One of the key tools used is the seismometer, which detects even the smallest movements in the Earth's crust. When strategically placed along the fault line, these instruments provide valuable data about the location, depth, and magnitude of seismic activity. This helps scientists better understand the stress building beneath the surface and predict where and when an earthquake might occur. In addition to seismometers, scientists also use advanced geodetic technologies like GPS and satellite-based radar to monitor fault activity. These technologies are so precise that they can detect movements of the fault line down to a few millimeters. This gradual movement, known as fault creep, occurs between major earthquakes and contributes to the buildup of stress along the fault. By tracking these small shifts, scientists can gather critical information about stress accumulation, which can aid in predicting future earthquakes. The ongoing advancements in technology and research are essential for improving earthquake forecasting and preparedness, helping to safeguard the lives and infrastructure of those living near fault lines. While technology has significantly enhanced our ability to study seismic events, field research remains critical to fully understanding the San Andreas Fault. Scientists examine rock formations, fault scarps, and other evidence of past earthquakes to build a historical record of seismic activity. This data helps model both past and future earthquakes, aiming to minimize their impact on people and infrastructure. By improving our knowledge of how earthquakes happen, we can better prepare for them. To understand why some earthquakes are more powerful than others, it's important to grasp the architecture of our planet. California has some of the strictest building codes in the world, designed to ensure that new structures are earthquake-resistant. However, older buildings and bridges pose challenges as they may not meet current standards. Fortunately, there are ongoing efforts to retrofit these structures, making them more resilient to earthquakes. This involves reinforcing buildings, bridges, and other infrastructure to withstand the forces of a major earthquake. Retrofitting is a crucial part of California's overall earthquake preparedness strategy. In addition to infrastructure improvements, authorities focus on early warning systems and emergency responses. These systems are vital in reducing the impact of earthquakes by providing crucial seconds to minutes of warning before the shaking starts. In California, agencies like the United States Geological Survey, USGS, and the California Office of Emergency Services collaborate to offer early warnings. While the warning time may be brief, even a few seconds can save lives and reduce damage by allowing people to take safety measures and activate emergency protocols for critical infrastructure. A lesser-known but important aspect of seismic activity involves dried lakes or paleo lakes, former lakes that have since dried up due to natural or human causes. These lakes offer valuable insight into past seismic activity. When a lake dries, the sediments that settled at the bottom remain, creating layers that record geological and environmental events. Scientists study these layers to track the history of earthquakes in the region, analyzing the magnitude, frequency, and intensity of past events. When a major earthquake occurs, seismic waves cause lakebed sediment to liquefy, creating distinct layers known as turbidity deposits. By examining these deposits, scientists can establish a timeline of past earthquakes and identify patterns that shed light on the region's seismic history. In addition to providing historical data, dried lakes can also influence current stress levels along nearby fault lines. The rise and fall of groundwater in these areas can affect the buildup of stress. For instance, when groundwater levels drop, it can reduce the pressure on the Earth's crust, potentially increasing the likelihood of seismic activity. Conversely, rising groundwater levels can alleviate stress and reduce the chances of an earthquake. A study published in Nature found that major earthquakes in certain areas tended to occur when nearby bodies of water were filling or full, but with the lake drained for over 3 centuries, the dynamics may have shifted. Dried lakes also impact fault line stability. When a lake dries up, the removal of water weight can cause the Earth's crust to rise or sink, depending on underlying geological conditions. This movement can alter the stress regime along nearby fault lines, potentially triggering seismic activity. Thus, dried lakes play a complex role in influencing both the timing and severity of earthquakes. One benefit of studying dried lakes is that they provide insights into the region's historical hydrological conditions. By analyzing sedimentary layers, scientists can track environmental changes over time, whether due to climate shifts or tectonic activity. This data is essential for understanding the long-term evolution of fault systems and improving earthquake hazard assessments. While dried lake studies offer valuable information about past seismic activity, they also highlight the increased vulnerability of certain areas to earthquake damage. Regions surrounding dried lakes are more prone to intense shaking during an earthquake because sedimentary deposits can amplify seismic waves. The level of vulnerability depends on the characteristics of the sedimentary layers, with some areas more susceptible to ground shaking than others. Scientists consider these factors to improve hazard assessments and develop effective earthquake preparedness strategies. The combination of advanced technology, field research, and studies of dried lakes has significantly deepened our understanding of seismic activity and fault dynamics, ultimately enhancing our preparedness for future earthquakes. Understanding the San Andreas Fault and its behavior is key to reducing the risks posed by earthquakes. By monitoring seismic activity, analyzing past events, and studying the geological factors that influence fault dynamics, scientists aim to improve earthquake forecasting and enhance mitigation efforts. These efforts include strengthening infrastructure and refining early warning systems to protect people and property. Historical context and preparedness. Gaining insight into the historical context of seismic activity along the San Andreas Fault is essential for improving earthquake preparedness. By studying past earthquakes, scientists can identify patterns that help predict future events more accurately. This historical perspective provides valuable lessons that shape current earthquake preparedness strategies. One important method for studying past earthquakes is paleoseismology, the study of ancient seismic events as preserved in the geological record. Paleoseismology plays a crucial role in California's earthquake preparedness by offering long-term insights into fault behavior. These findings have influenced infrastructure resilience by driving the development of strict building codes. For example, paleoseismology has informed retrofitting practices, which are vital for reducing the vulnerability of older structures to seismic activity. Retrofitting, reinforcing buildings and bridges, has been instrumental in minimizing casualties during earthquakes. A prime example of the benefits of retrofitting can be seen in the aftermath of the 1933 Long Beach earthquake. In response to that disaster, retrofitting became a cornerstone of California's approach to earthquake risk reduction. Public education and awareness. Public education and awareness campaigns have also played a significant role in California's earthquake preparedness efforts. Authorities have focused on educating people through earthquake drills, community resilience programs, and safety guidelines. These initiatives teach people how to protect themselves during an earthquake and safely evacuate. By promoting effective response strategies such as drop, cover, and hold on, these campaigns save lives by ensuring people know what to do during an emergency. Technological advancements. Technological advancements have further improved California's ability to respond to earthquakes. Modern monitoring systems provide real-time data that aids emergency response and supports early warning systems. One such system is Shake Alert, which uses seismic data to alert residents and businesses before the shaking from an earthquake reaches them. Even a few seconds of warning can allow people to seek cover, potentially preventing injuries and saving lives. By combining paleoseismology, public education, and technological innovations, California has become a leader in earthquake preparedness. Continuous research and proactive measures have helped the state remain resilient in the face of ongoing seismic activity. These efforts highlight the effectiveness of careful planning and preparedness in reducing the risks posed by natural disasters like earthquakes. By learning from the past, using cutting-edge technology, and educating the public, California continues to make strides in protecting its residents from the potentially devastating impacts of future earthquakes. What do you think about the San Andreas Fault? Share your thoughts in the comments below. If you enjoyed this video, make sure to like, share, and subscribe to our channel. Also, check out the video on your screen. You're sure to enjoy it.